Chemists spend a great deal of their time separating and purifying the chemicals that they make. And filtration is one of the basic tools that chemists use to get to their final product. In simple terms, filtration is the process of separating solid particles from the liquid or gas that they are suspended within. It's something we do every day, and in fact it's happening right now in my garden fish pond. Beneath the surface, underneath that fountain over there, water is being pulled into the pump. And blocks of foam like these are taking the dirt out of the water and keeping it clear so that I can see my fish. Filtration also happens every time you drain your vegetables in the kitchen or enjoy a filter coffee. And you also benefit from it every time you turn on a tap and see clear water pouring out. So join me as we uncover the secrets of this important separation technique. Welcome to the first of our videos looking at key separation techniques used in chemistry. If you're starting your course from scratch, you might want to check out our overview video, which is linked above, because today I'm going to focus on just one of those techniques. And today I'm going to take you through the key aspects of the process of filtration in a chemical laboratory. We'll start with the key terms and a bit of the theory. I start out with a mixture of an undissolved solid and a liquid. In this case, I have a mixture of soil and tap water, similar to what you might find at the bottom of a garden pond. My goal is to separate this into clear water, which we'll call the filtrate, and the solid parts, which we'll call the residue. To do this, I'm going to use a sheet of filter paper and a funnel. Now, you might hear the filter paper being called a filtration substrate elsewhere, but at GCSE, we're generally going to stick to calling it filter paper. To prepare the paper, I simply fold it in half once, then again, and then I open up one of the little pockets I have created, and I'm going to sit that into my funnel. To help it sit snugly, I'm just going to add a little bit of the liquid part of my mixture, which in this case is just some distilled water. The paper works because it's actually full of tiny holes. They're too small to see with the naked eye, but under my microscope, the paper looks like this. The fibres of the paper overlap, and what I end up with is a much smaller version of that spongy pad that you saw that was keeping my fish pond clear. With my filter funnel seated over my conical flask like this, I just stir up my mixture a little, and then I slowly pour it into the filter paper. And what we see is that slowly clear water is coming out here, and that's the filtrate, and in the top I've got my mixture, and eventually trapped in my filter paper will be my residue. The holes in the filter paper are too small for the soil particles to pass through, so they get trapped while the liquid part drips down into my flask. Now, you might be asked to draw a labelled diagram of this process, so we'll just go over those key parts. The equipment is a funnel, sometimes called a filter funnel, the filter paper, and the conical flask. You might add a beaker for holding the original mixture, but otherwise all we have to do is label the starting mixture, the residue caught in the filter paper, and the filtrate that's passed through it. As a pencil diagram, such as you might draw it, it would look like this. Again, I have the equipment, that is the filter funnel, the conical flask, and filter paper, and I have the chemical parts, which are my mixture, my filtrate, and my residue trapped in the filter paper. Now some important points. The filter paper can only prevent particles larger than its holes, or pores, as we should call them, from passing through it. This means that anything smaller than those pores ends up in my conical flask. This looks reasonably clear, but is it pure? Well, no. That original mixture of soil and water will have had some particles in it that are too small to see with the naked eye, but they have made it through the pores in the filter paper, giving this a slightly cloudy look to it. Now also, those pores are far too large to prevent bacteria or dissolved substances from getting through, and my original mixture will certainly have had some of those in it, and so I certainly wouldn't be drinking this water. And this brings us on to the next important point about filtration: pore size. What pore size do we want within our filtration substrate? Well, the answer is it depends. It depends on what you want to remove from your mixture and the rate at which you want to do it. In my pond, I just wanted to be able to see my fish, and so those holes in my filter block were more than small enough to stop large particles of soil from circulating. But if I want crystal clear water, I'm going to need something with a lot smaller pores. To separate all of the fine particles, I've already said that I'm going to need a sheet of filter paper. But in fact, not all filter papers are equal. And in fact, I have 3 different ones here in front of me. And I'm going to put a similar mixture of soil and water into each. So, first I'll make up the solutions. I have 3 pre-weighed samples of soil and 3 beakers, each containing 80 millilitres of water. I'll add the soil to each of them, give them a stir, and then I'll pour each into the filters, and we'll wait and see what happens. Now you'll notice that this one on your right here has already finished, and all 80 centimetres cubed of liquid have already passed through it, whereas these 2 are still going. And that is because these filter papers have got a significantly smaller pore size than this one has here. And as a result, yes, they're trapping more particles, but it is taking longer for even the water to get through. I'll put up the times for the 3 filter papers and their pore sizes in this table here for you to have a look at. All 3 filter papers have now finished filtering through 80 centimetres cubed of liquid. I'm going to remove the funnels and just store them over here. And then we can have a look at the solutions that we've been left with. Now, these 3 filtrates here, I can see by eye that that one is slightly cloudy. This one looks clear, and so does this one. But we're only going to know for sure once we get samples of these 3 filtrates under a microscope and have a closer look. So I'm going to take a little sample of each one. And we're going to have a look at a single drop of each of these samples under the microscope. Looking under the microscope, we can clearly see small particles in the first sample. The other 2 samples, I wasn't able to find a single particle with my microscope here. So I think we can conclusively say that that first one that filtered quickly did so at the expense of allowing particles through that ideally we would rather had not ended up in with our filtrate at the end. And this is the balance that we're always going to have with filtration. We balance the speed of the process against the size of the particles that we allow to pass through. But remember, there are some things that no laboratory filter paper can stop, and they are dissolved substances and bacteria. So, in summary, you should know a few examples of ways in which filtration is used. You should be able to draw and name the apparatus needed for filtration in the lab and use the key terms mixture, residue and filtrate correctly. You should be able to explain why we cannot use filtration to separate a dissolved substance from a solution and why water that has passed through a filter paper is not necessarily safe to drink. If you would like a summary of the key points and access to some exam-style questions on filtration, then head over to my Patreon page where you'll find a free worksheet to help you. And if you've got any specific questions, then please ask them in the comment section below and I'll get back to you with answers. Happy studying, and I'll see you next time.